So hello everyone. You got myself, Nathan Price, as well as
Dean Summer.
Dean Summer. I'm Nathan Price. I'm the Dairy Ingredient Coordinator here at the Center for Dairy Research. I've been here since last May, so about 7-8 months. In my role, kind of coordinate pilot plant. If you guys want to come in and run some trials, we can get that organized for you. Today we're going to talk about dairy ingredient manufacture. Dean, do you want to run through?
Sure. So I'm Dean Summer. I've been here going on 19 years at the center. I'm a cheese and food technologist. I work a lot in the cheese, but I also do some work on the whey processing area as well, which we'll be talking about quite a bit today. Prior to that, I worked at one of the largest Wisconsin cheese and whey processors for 18 years. So have a fair amount of industry experience in this area. And I'll try and share as much as I can of that with you guys today as we go through this presentation.
So to get started with this talk, we want to look at the composition of milk and whey. You can see for cow's milk here, it's approximately 4% fat, around 3.1% protein. The largest component is lactose, around 5%, and ash, around 1%. Comparatively, if we look at whey, once again, the largest component is lactose, around 5%, around 1% protein, and around 1% ash. Now the biggest thing I want to point out here is the composition of water. You can see water is 87% of cow's milk and 93% of whey. Since this has such a high concentration of water, it is a perishable product, so it will spoil quite quickly. So our goal in manufacturing into dairy ingredients is to remove that water and create a shelf-stable product in the powder form. So once again, biggest point, how much water is in milk as a starting material. So for a demonstration we have here, we have our gallon of milk and how much water that relates to.
So this is how much water is in that 1 gallon of milk that Nathan just held up.
And if we can dry that down to a final powder form, this is how much non-fat dry milk we'll get. And if we break that down even further into our fat, our protein within our gallon of milk, our lactose, and then our minerals. So you can see we go from this large of a volume into something that'll fit into a quite small jar.
And if it's on the whey side, if we're just going to dry into sweet whey powder, this is how much sweet whey powder we get out of that whey from 1 gallon of milk. If we made cheese, we would get about this much cheese out of that gallon of milk, about 0.8 pounds of cheese out of that gallon of milk. And if we were going to do just whey proteins, we'd get about this much whey proteins. Ash and minerals, about this much, primarily calcium phosphate. Lactose, a lot of lactose in milk, about almost 5%, so we're getting a fair amount of lactose there.
So hopefully this puts it into perspective how much water we are removing, and is very critical for converting that milk into a finished powder. Okay, so it must be. Okay, now we can look at the composition of powder. Biggest point here, we can see only 5% moisture within our whey powder and 3% moisture within our non-fat dry milk from that original 87 to 93% as our starting materials.
Notice especially in the composition of powder, both the non-fat dry milk on the left and the whey powder on the right, how much lactose is in there. Just a tremendous amount of lactose, 73% in the whey powder, 51% in the non-fat dry milk. So lots of lactose in the system, and a fair amount of ash too, 8% in both cases. So quite a bit of minerals, quite a bit of sugar, lactose.
So now we'll get into why don't we just dispose of whey. This has a large economic value. I remember back when I was a kid, I grew up on a dairy farm, and there was a cheese plant about 3 miles away, and I can remember roaming around the countryside and then disposing of the whey onto fields. That was only 25 years ago or so. One reason we don't want to dispose of it, there's huge volumes. It is also very expensive to treat in a wastewater system, has very high COD and BOD value, so would be tough to digest within wastewater systems. Also, it's very expensive to land spread. You know, you got to pay the driver to drive the truck. You also have to maintain the truck as well as get it onto that field. One important thing to consider is there's not enough outlet to feed as a liquid to animals such as pigs. It's profitable to process and sell, but it requires huge economics of scale. So you need very large equipment, which we will go into detail further on in this presentation. Also, the value of whey can be a significant addition to the processing plant, as it can contribute up to 15% to the dairy farmer's milk check.
So a few notes on that. So I'm a heck of a lot older than Nathan. I grew up also on a little dairy farm, but back in the 50s and in the early 60s. Back in those days, the milk truck, and we had canned milk. The canned milk truck would stop to pick up our cans of milk, but then they would drop off whey because we had pigs as well, and we had mixed the whey with grist, which was ground up corn and other grains and vitamins and stuff, and feed that to the pigs, and that was a very good pig food. So back before the widespread processing of whey into human food, which only began pretty much in the 1970s, pig feeding with whey was probably the dominant way to dispose of your whey. You can't just dump it in streams like they did probably in the early part of the 1900s, because it would really pollute the streams and rob the streams of oxygen and things like that. It is expensive to land spread, and it's problematic here, especially in the upper Midwest, like right now when all the land is frozen and covered with snow. So that's not a good outlet either for the most part. We talked just a minute ago about how much water is in whey, over 90%, 93 to 94%. That's why this second to the last bullet point about needing huge economies of scale comes into play, because we have to remove all that water if we're going to ultimately convert the whey into a powder form of some form or another. And this last bullet point about contributing up to 15% of dairy farmers' milk checks, the way that the means that the dairy farmer's milk check is calculated includes a contributing factor of whey. So let me explain that. So USDA nationwide establishes a minimum price for raw milk at the farm level. And when they do that, they compute the current value of milk fat, the current value of protein, and the current value of what they call other solids, which is the lactose and the minerals, and that's the solids that's in whey. And all those factors go into calculating the price of raw milk at the dairy farm. So if I have a plant, I have to pay my farmers the value of the whey in their milk, whether or not I capture that value. So if I just take my whey and dump it on the field, I get no return for it. In fact, it's a cost because I got to truck it out there and maybe rent the land. But even if I'm just disposing of the whey, I still have to pay my farmer the USDA calculated value of the whey that was in their milk. So, boy, it really behooves cheese processors to try and capture as much value from their whey as they possibly can.
We can look at this slide here. Another thing why we want to process the whey. We can look at the distribution of the milk components between the cheese and whey. You can see the water component majority goes to our whey. We look at the total solids. This is something that you may not realize, but around greater than 50% goes to the whey. So a larger majority of our original milk solids go to the whey and not to the cheese. You can see for the casein, the majority of the casein goes to the whey. There is a small fraction that is cleaved off by rennet called glycomacropeptide that goes to the whey. You can look at our fat, the majority goes to cheese, lactose, vast majority goes to our whey, calcium, kind of an even distribution with a higher component going to our cheese.
Yeah, so like Nathan said, in terms of total solids, it's close to 50-50. 50% goes to cheese, 50% goes to whey, but different solids go different directions. The majority of the fat, the majority of the casein, about 90% of the fat, about 80% of the protein is going to end up in the cheese, but the majority of the lactose is going to end up in the whey. So yes, it's 50-50 solids, but it's not equal types of solids. Different solids partition different directions.
So yep, we can see here 50% go to the whey. And these solids have different values, so that's a very thing to consider. Our protein have a higher value, our fat have a higher value, with our lower value components being our lactose and minerals. So if we look at whey to whey powder, if we're in a plant and we process 1 million pounds of milk a day, that will result in around 900,000 pounds of liquid whey at approximately a 6% total solids. If we're bringing in 20 tanker loads of milk, 18 tankers loads of those milk will be turned into raw whey, with only around 2 tanker loads being cheese. And after drying, that'll equate to about 1 truckload of finished whey powder, with the remaining being water. We can get that point across here. We look at our 20 tanker loads. We convert that into cheese. We're going to have 2 semi-loads of cheese, 17 tanker loads of water, and 1 tanker load of finished powder. If we look at the same scenario where we're going to process our milk into non-fat dry milk instead of whey, we have our 20 tanker loads of starting milk. We're going to remove around 2 tanker loads of cream, which will be used in butter, whipped cream, or ice cream applications, and will result in around 2 semi-trucks of non-fat dry milk, with around 16 tanker loads of water removed. So why are we interested in removing the fat prior to making whey and milk powders? One important thing to consider is the value. We get higher value from that fat in cream. These numbers aren't up to date. I think cream's around $3.
Well, $3 a pound right now.
Right now, so our numbers are...
Fat is worth $3 a pound.
Yep. But if we're going to sell that fat in our non-fat dry milk or whey powders, we're going to get a lower value for that. So we can get a higher value selling it as an individual component within cream. A very important thing to consider is shelf life. If we look at the shelf life of whole milk powder, we only have a shelf life of around 6 to 9 months. But if we remove that fat and make it into non-fat dry milk, we'll have a shelf life of greater than a year. So fat can really affect the shelf life when it's in the final powder format, as well as issues with further processing for making milk protein concentrate or whey protein concentrate products that have higher protein concentrations. The processing within the UF can be affected by that fat content.
So just kind of a summary of that, the fat is your friend, your economic friend, especially when you capture it in cheese or capture it in cream. But it's your enemy if it isn't captured and ends up in milk powders and whey powders. The exception, of course, being whole milk powder. But in terms of non-fat dry milk and all the various whey powders, fat is your enemy, because not only have you lost value, but fat oxidizes during storage and leads to off flavors. It also affects functionality of some of your finished milk and whey fractions and products, like things like foaming and gelation and things like that. So you want to capture it in your cheese and your cream. You want to avoid having much in your finished dry powders.
So now we'll start getting into the processing that it takes to remove that water from our raw materials. So the basic processes that we're going to utilize for water removal to concentrate the solids are evaporation. We can also fractionate milk and its components out into a bunch of different components. We can run our milk through We'll have a demonstration here shortly of a sieve. We can separate the water from the proteins, from the minerals, from the lactose.
So when in any separation process, you have to leverage differences in what you're trying to separate. In this particular slide, in the lower right-hand side, you see the water, the protein, the minerals, the lactose. Well, primarily, the separation here is going to be based on size of the molecules. In this example, protein would be the largest molecule by far. Water would be the smallest molecule by far. And lactose and minerals will be in between. So much like a sieve will separate sand or gravel based on the size of the pebbles, the fractionation techniques we're going to talk about in a little bit will separate these based on size as well.
Mm-hmm. So why are we interested in removing all this water and process our raw perishable material into a powder? Storage is a big thing. We can extend the shelf life of milk in its raw state. Microorganisms love it, and they will spoil it quite quickly. So the shelf life of liquid milk is quite short, less than a week. While in our powder form, we can have quite an extended shelf life, 6 to 18 months. You can see here in the slide it says shelf life of a year or more. Also, shipping long distance, this is a very important thing to consider. Remember, we had our 20 tanker loads of our raw milk. If we're going to ship 20 tanker loads of raw milk, overseas, it's going to be a large value in shipping. But if we're able to condense that powder down into, just one truck, we can reduce shipping costs dramatically. As another thing here, U.S. dairy industry exports approximately 50% of our dairy solids overseas, and that is critical for our health. We're able to get value for that whey, which we weren't utilizing in the past. And the majority of dairy exports are currently milk and whey powders.
So most of those exports are, a good share of them at least are going to Asia, so they're going on ships across the Pacific Ocean. Last week, I just saw the data for 2021, and the U.S. dairy industry exported approximately 17% of our dairy solids, and most of that was whey and milk powders to places like China and Korea and Japan and other countries in Asia. So this is critical to our industry because all those, if we didn't have those export markets, those products would back up in our inventories here in the U.S. and that would depress milk prices. So this exporting of dairy products of various types is critical to the economic health of the U.S. dairy industry.
So now we're going to get into fractionation with membrane filtration. This is a way we can separate different components based on their size, molecular weight. So why are we interested in fractionation? The value of components is greater than the value of milk or whey. So for example, our protein has a high value. If we're able to separate that from our lactose and minerals, we can get higher value for that. As well as the individual components have unique qualities such as nutrition and functionality. And with this fractionation method, we can get more value for our products and get more value for the dairy farmers as well as the manufacturers.
So when we say functionality, what do we mean? We mean, and we'll show you some later, but things like emulsions and foams and things like that. So it somehow functions in a way that is critical for the creation of certain foods or certain ingredients that are used in foods.
So the equipment that we're going to utilize to fractionate milk and whey is membrane filtration processes. These were originally developed in the 1960s, and they're pressure-driven separation using semi-permeable membranes. Dean will have a kind of a display of what these membranes look like. Spiral wound are the most commonly used within the dairy industry. For pore size and pressure, they are related. So for the smallest pore sizes with reverse osmosis, we're only removing water. And due to that small pore size, we're going to operate those at the highest amount of pressure. With nanofiltration, there's a little bit larger pore size, so we can use a little bit lower pressure than reverse osmosis. Ultrafiltration, we have a larger pore size even yet. in microfiltration with our largest pore size, so that'll be operating at our lowest pressure. So we'll get into a couple demonstrations here about how membrane filtration operates. For our first demonstration here, we're going to use sieves to separate milk components, and this is the basic principles of how membrane filtration works. So within these sieves, you can see this one has the largest pore size, this one a little bit smaller, this one even smaller yet, and our final one will have the smallest pore size. To mimic the fat or the components within milk, we'll have these beads. So this bead will represent our fat. This kind of colorful bead, we have different colors of this one, will represent our proteins. This one, our white bead, will represent our lactose. These different color beads, they're small, hopefully you can see them slightly. They'll represent our minerals, and our smallest silver bead will represent water. So if we pour our conglomeration of all the different milk components into our sieve, and we shake it a little bit, try to mimic the membrane filtration technology. In our first sieve, we collected only fat and our protein. Within our next sieve, which has a little bit bigger or smaller pore size, we didn't really collect anything, so we really didn't do any work there. When this bead, or in this sieve, we're falling, we collected our lactose, our water, and then this smallest one, which would mimic reverse osmosis, we only removed water. So that's kind of the practical demonstration of how membrane filtration works. Hopefully that kind of gives you a better idea of exactly how this works. There are quite a few videos online which we'll include within this demonstration that maybe will visualize that concept a little more or a little better than this demonstration, but hopefully this helps a little bit.
So we want to talk a little bit about membrane filtration and how it works. So what I have here in my hand is called an element. And if you look at the element on the end, it's kind of like a paper towel with a cardboard tube in the middle, and in the paper towel, this would all be paper towel, or if it's wrapping paper, wrapped around the tube in the middle. But these are called spiral wound membranes, and these are the workhorses of the industry today. And the membrane material is just spirally wound around this tube, just like a paper towel would be, or toilet paper around a tube. And what happens is, on one end of the tube, we force the milk or whey in, and as it passes through, the membrane material separates it out, and the permeate ends up going into the center section and coming out this end. So that would be our milk permeate or our whey permeate. And the retentate comes out here and is captured, and that's our retentate. So spiral wound is talking about the fact that the membrane material and the backing is spirally wound around this tube. The tube is where the permeate will come out. The rest of it is where the retentate will come out. And again, these are the workhorses of our industry. The actual pores in the membrane are so small, you'd need a microscope, very powerful microscope, just to see them.
First one to look at is nanofiltration. So we can see in our image here, we're going to permeate our monovalent ions such as our sodium, chloride, and potassium, as well as some acids and monosaccharides. What we're going to retain within this membrane are our divalent ions such as calcium, magnesium sulfate, and sugars, protein, fat, and microorganisms. Our usual operating pressure within these NF systems are between 150 to 400 psi. And the theory here is the charge in membrane surface versus the charge of ion. So we can affect or change the surface of our membranes to maybe reject our sodium or chloride more effectively.
So again, here's our nanofiltration membrane, and you can see in this case the water can pass through. Monovalent means one charge, so something like sodium or chloride, salt, those are one charge. Divalent means 2 charges. That would be like calcium, which is +2. So in this case, the 1 charge, which are smaller, can also go through. But the 2 + 2 charge, they're bigger and they have that different charge. They're rejected. It's called being rejected by the membrane. But the lactose is bigger yet, and that gets rejected. And the protein is much bigger yet, and that totally gets rejected.
So the next membrane we'll look at, and this is a workhorse within the dairy industry, is our ultrafiltration. We permeate our water through our membrane, our minerals, as well as our lactose. The thing we're trying to concentrate with these membranes is our protein. So we're able to concentrate the protein and remove our lactose and minerals through this process.
So when you hear of products called whey protein concentrate, WPC, this is the process that we're going to use to make most of the WPC products.
We usually run at a lower operating pressure between 100 to 150 psi. As we can tell what's being rejected from this membrane, it has a larger pore size. So with that larger pore size, we don't need as much pressure to separate these different components. And our theory here is our shape, charge, flexibility. Molecular weight is a big factor. Secondary membrane layers determine the ability of our different components within milk to separate through this membrane. And our final fractionation membrane process we'll look at is microfiltration. You can see here the permeate with these membranes are what passes through our water, minerals, lactose, on our smaller and larger proteins, while what is being concentrated within these membranes or retained or not passing through our membrane is our fat and microorganisms. One thing that we'll look at a little bit later is the type or different types of membranes that are utilized within these systems. For spiral wound, they're commonly, or not as commonly used for removing microorganisms, but ceramic membranes are used to, microfiltration membranes are used to separate out microorganisms more commonly.
So just to review again, those materials that pass through the membrane, in this case these ones and this one, that's called permeate because it permeates or passes through the membrane. Those molecules that can't fit through and are rejected, like the larger proteins, fat, and microorganisms, that's called retentate. They're retained by the membrane because they can't pass through. So one last point on the small and large proteins. It turns out that in milk, 80% of the proteins are casein, and they're big. Most of them end up in the cheese if you're making cheese out of it. The smaller proteins are whey proteins. They are much smaller than the casein or cheese proteins. So if this is milk, which has 80% casein and 20% whey proteins, the whey proteins can pass through this microfiltration membrane, but the casein, because they're bigger, cannot pass through and they're rejected and they stay in the retentate.
Once again, this has a larger pore size within our membrane, so we operate at a lower operating pressure of 5 to 50 psi. Theory, size determines the ability to cross this membrane. So now we'll look at ways to remove water for the production of dairy ingredients. So why is it important to remove water? Well, we want to get that shelf-stable product, but so here are some of the ways that we can do that. Approximately 60% of our water removal can be used with membrane filtration. This is our least expensive way to remove water, but we're limited in how far we can go. Osmotic pressure can limit how much water we can push through our reverse osmosis membranes. Our next step to remove water is evaporation. This is our next least expensive way to remove water, but once again, we're limited to how far we can go. Once we get too high of a viscosity, we're not going to be able to pump it or move it through our evaporating system. Our final step in removing water is drying. This is our most expensive. We need the largest equipment, but it is necessary to take it from a liquid, flowable product into a final product that is in its dry form in a powder. And these are used in series with membrane filtration removing approximately 60% of the water, evaporation around 25%, and drying removing the final 15% of the water from our products.
So put another way, the way the industry kind of thinks about it, at the floor level. I'm familiar with whey, so let's say we get whey. So the whey comes off the cheese making. It's approximately 6% solids, 94% water. So 6% solids. So we could go through an RO, a reverse osmosis membrane, and it can take it from 6% solids up to in the neighborhood of 30% solids. But that's as high as it can go because of osmotic pressure and other issues that Nathan mentioned. Then we would go to evaporator, and that'll take it from 30% solids up to about 55% solids or so. I'm just giving you rough numbers. And then we crystallize it in the case of whey, dry sweet whey, and go to a dryer, and that'll take us up to around 95, 96% solids, because even though it's a powder, there's still, and you want it, a small amount of residual water left in the powder. So like Nathan said, we typically do it in series because it's cheaper to take out as much water as we can with membrane filtration, and then next evaporator and evaporation, and then finally dryer to take it to a powder form.
Yep. So we'll look at the first step within this series, and that is our reverse osmosis membranes. We permeate only water within this system, which you can see in the diagram. Our water is small enough to pass through the pores within our reverse osmosis membrane. But once again, we have those smaller pores within this membrane, so we have to use higher operating pressure. So we use pressures around 200 to up to 1200 psi. The retentate from this stream is basically everything else besides water that you're feeding the reverse osmosis membrane.
By the way, this is the same technology that they use to take seawater, which is salt water, and make drinking water out of it. In some coastal cities around the world, they use RO to separate some drinking quality water out of the seawater. And many of you maybe have a small RO unit on your tap water at home to remove unwanted minerals or other things that could be in your well water type of situation.
Yep. And the pores within these membranes are so small you need a scanning electron microscope to see them. There are some compounds that can kind of mimic the tetrahedral structure of water, and they may be able to pass through. They're really quite small compounds such as urea, some non-protein nitrogen, as well as methanol.
In a processing plant environment, this water that you can collect from RO is valuable to you because it's extremely soft, because you've taken all the minerals, the calcium phosphate out of it. So this is highly sought after water in most processing plants for cleaning and CIP makeup water, for boiler makeup water, anywhere where you want really soft water with hardly any minerals in it.
Yeah, basically utilize the water that's in your original milk to help clean equipment, reduce your dependency on well water, and make it more sustainable. So the next process we'll look at is evaporation. This is used to concentrate the milk, whey, or permeate. And it is required to make products such as non-hydroscopic whey or permeate powder. This process uses vacuum, so we can remove water at temperatures below our boiling point. So we can use temperatures quite significantly less, and that can lead to less protein denaturization, less precipitation of our calcium within our different feed streams, as well as lower energy costs. That's a big factor you need to consider, is ways to reduce energy costs in your footprint, as well as less cooling required for the final product.
So now we're talking about evaporation, and again, I come more from the whey processing world, but now we're into the economies of scale. Even relatively small plants can afford ROs, and many have them, to pre-concentrate their whey because they're going to ship it to someone else for further processing, and that's very economically feasible, even for certainly medium-sized plants, but even fairly small plants. But now when you talk about evaporation, you're typically talking just monstrously large pieces of equipment, very capital expensive, very difficult to run, meaning it takes a lot of technology and a lot of know-how. So most cheese plants would not have an evaporator to concentrate their whey unless they're a very large cheese plant, because you need literally millions of pounds of whey per day to justify installing the evaporator in your facility.
Falling film evaporators are most commonly used within the industry. So the product falls down our tube, as well as whereas the water is being pulled out with our vacuum. Gravity is the driving force, and usually multiple effects are possible. So as we go through one effect to another one, we can have higher vacuum, as well as our temperature is being decreased because we're losing heat through those processes.
So the way it works, so this large vessel here is called the calandria, and there's a tube bundle in there. So there's smaller tubes. You can kind of see them. Oh, you can't see them at all in this photo. Hopefully in a future one. But there's little smaller tubes in there, and the product comes in the top, and it falls down the outside wall of those tubes, or the inside wall of those tubes. Sorry. And surrounded that is a heated medium, which causes the water to evaporate, and the water is removed as vapor and then recondensed. And when it gets down to the bottom, and this is the condensate, the water coming out, but the concentrated whey comes out and goes to the next part of the evaporator. So it's essentially using heat and vacuum to evaporate water from the whey or from the milk if you're doing milk.
So the next process we'll look at is drying. Spray dryers are most commonly used to remove water from dairy products. The general step is evaporation, heat air. So we have very hot air as the concentrated product is being sprayed into a chamber after the product is atomized. And the mixture of the hot air and the atomized product helps aid in the removal of water. And then we have cyclones to separate the powder from our drying air. This is commonly a two-stage process where we have belts and mats and etc.
So think of this dryer. So we're talking about a spray dryer. So what the heck does that mean? So you've all operated a garden hose in your yards at home or in your gardens at home, and you have a nozzle on the end, and the water comes out, and you can form a fine mist if you want at a certain setting. Well, that's what we're intentionally trying to do with a spray dryer. They'll have a nozzle at the top of the dryer, and it's a very small orifice or opening, and there's very high pressure pushing that liquid whey or liquid milk to that nozzle, and you're going to form a mist, and that mist is typically going to fall in a column of very hot air. And as it does it, the water is evaporated and removed, and now you've got a powder, and the powder will fall to the bottom of the dryer and then get conveyed to the next part of the processing step in the dryer.
And another important point, Dean brought this up when we had this course back in October of last year. Just the economies of scale for evaporation and spray dryer. You know, there's 125 cheese plants within Wisconsin. How many do you think have dryers and evaporating systems? Only 12. So,
and they're all big
yep.
big operations.
Yep. There are different types of dryers, which you can see on this slide. Bunch of different kinds. The main two that are used within the dairy industry are our spray dryer as well as our fluid bed. But just wanted to point out that there are different types of dryers. So we'll look at the manufacture of our dairy ingredients from milk. We're going to focus on 5 main products: our milk protein concentrate, milk protein isolate, non-fat dry milk, and a whey protein concentrate and whey protein isolate. And we'll break down how they are manufactured. The first one we'll look at is non-fat dry milk. So for non-fat dry milk production, we take our milk in, we'll separate that to remove our skim milk. Then we'll pasteurize that. We'll run that through an evaporator to get up to our 45-50% total solids. For this diagram, it says cooling and storage. Typically, you can feed that directly to your dryer, where it'll be spray dried and get to your final powder format. You can change the drying parameters to get agglomerated or instantized, depending on what the end goal of the product that you're looking for.
So one critical part of this, and we kind of alluded to it before, is this separating into skim milk. Again, in this case, you want as little fat in the finished powder as possible. So you want to separate, we call it separating as clean as possible, meaning, ideally the skim milk would have 0% fat in, but that's not technically feasible with the technology we have today. But we can get it down to around 0.06, 0.07% fat. Again, economically, that cream is going to be more valuable than the finished non-fat dry milk powder, but also from a powder quality and a storability and a shelf life, the less fat we have in the powder, the better. So this step of separating the fat from the skim milk is really important in this process.
If we look at the composition of non-fat dry milk, is around 37.3% protein on a dry basis. Our moisture is usually around 3.5%. The majority or the highest component within non-fat dry milk is lactose, around 50%. Fat, around 1%, and ash, around 8.5%. We can look at the shelf life of non-fat dry milk. If you instantize, or non-instantize has a greater shelf life of 12 to 18 months. If you have an instant product, more surface area within that product will have a shorter shelf life of 6 to 12 months. You got a point, Dean?
Well, I was just going to say, and I don't know if we cover it later again, but instantized and not instantized. Instantized is an additional process when you're drying these powders. You typically re-wet them and then re-dry, slightly re-wet them, and then a finished dryer again, a finished drying step again. And when that does that, it makes the powder more wettable and more dissolvable. So if you buy, let's say, not many people do anymore, but non-fat dry milk in a box at a grocery store to make your own milk at home, that would typically be instantized, meaning you put it, you put some with water in a glass and you take a spoon and you whip it around and it very readily goes into solution. But if you took just regular non-fat dry milk that's made, in the industry, there's a ton of that. If you try and dissolve that in a glass of water with a spoon or a tablespoon, it's just going to kind of want to float on top and look at you because it's very hard to get it to go into solution. So depending on what the final use is of the non-fat dry milk, in some cases that's non-instantized is fine. But in some applications, you have to instantize it so it dissolves more readily.
Yep. If we look at the characteristics of non-fat dry milk, for color, it should be white to light cream. Flavor, clean and dairy. Titratable acidity, less than 0.14. If we look at our solubilities, we can adjust how much heat this product undergoes during the processing. So you can see different solubility indexes for low heat or a high heat spray drying process, as well as instantized. And also spray drying and compared to roller drying, you will have some differences in scorch particles.
So just to explain some of these, this heat intensity of the heat that the powder gets during the process or the milk gets during the process is really important. So let's say you're a cheese maker buying non-fat dry milk to use to make, say, low moisture part skim mozzarella. You definitely want low heat. This heat, the function of that is it tells you how much of the proteins have been denatured. So with a low heat spray dried product, it's going to be very little denaturation of the proteins, which for cheese making is good. If you have more heat, or a medium heat or a high heat spray dried process, that's going to have a lot more denaturation, which that's what bakers love. In the world of bakery, when they use non-fat dry milk in their various breads and stuff, they want high heat. But this speaks to how much denaturation of protein has occurred, which is really important to the end users and what they're going to do. Roller dried product is, unlike spray drying, is a very harsh treatment. That's why tons of denaturing of the protein has happened, and I don't see a ton of that product even in the marketplace anymore. Scorch particles, as the name implies, so you've got milk going through your dryer, you've got heat going on, you can get burn on the walls of the dryer, and then that burn on over time starts to flake off and get in your powder. Now, those are called scorch particles. They'll be kind of a light brown to dark brown to even sometimes almost black. It looks like somebody put pepper in your white powder. So you want as little of that as possible because it looks like foreign material in there. So with spray dryers, they have specifications for and ways to measure how much is in there, how much of these little burnt specks of powder are in your finished product.
The next product we'll consider is very similar to non-fat dry milk. This is a skim milk powder. This is defined by the Codex Alimentarius. Compares to non-fat dry milk, which is defined by the U.S. Code of Federal Regulations. The most important differences between these two products is skim milk powder can have the protein level adjusted down. And that may be done by using milk permeate or lactose to lower that protein on a dry basis. The final protein on a dry basis for skim milk powder, it has to be greater than 34%. And you saw within the last slide, for non-fat dry milk, it's typically around 37%. So you're able to add a little bit of milk permeate or lactose into that product to lower that protein content.
So why do you want to do that? So what's the valuable component in non-fat dry milk? It's the protein. And protein will vary seasonally. We know that protein in milk at the farm is highest in the winter, lowest in the summer. So non-fat dry milk made from winter milk is going to be really high in protein. From summer milk, not so much. But protein is what's valuable. So with non-fat dry milk, you just dry the milk as it comes in. And sometimes the protein can get over 37, you can get 38%, okay? But skim milk powder, like Nathan just said, you can add some extra lactose or milk permeate to your milk before drying to standardize or adjust down the protein level of the finished powder as long as it stays above 34%. So this would be a slightly less expensive product because you've taken perhaps some of the valuable protein out of the milk before drying it, and you've standardized the protein to the minimum amount needed as defined by the standards for skim milk powder, which is 34% minimum.
So the next product we'll look at is milk protein concentrate. The product that is used to make milk protein concentrate is ultrafiltered milk. So the first step is to run through ultrafiltration process to remove some of our lactose and increase our protein content. So UF milk during this talk will be defined as liquid milk that has a portion of the lactose and ash removed. It typically has the original casein to whey ratio of approximately 80-20. In the dry form, it is considered milk protein concentrate. So milk protein concentrate is the dry form of ultrafiltered milk. These are simply working definitions, as MPC is not greatly defined. Aadpi does have standards for MPC and MPI products.
These definitions, though, are important, and let me give you one good example of that. So in the U.S. today, as we sit here today, it is legal to use ultrafiltered milk to make cheese out of, or even to mix ultrafiltered milk with regular whole milk to make cheese out of in the U.S. Ultrafiltered milk is a liquid. Okay, it's concentrated protein, but it's still a liquid. Milk protein concentrates are the dry powder form of ultrafiltered milk. But even though ultrafiltered milk is legal to use to make cheese in the U.S., milk protein concentrates are not legal, not for standardized cheeses, meaning those cheese varieties that have a standard of identity. So it's kind of a little weird and tricky, but the liquid form is legal for virtually all cheeses in the U.S., but the dry form is not. So it's just a quirk of the current regulations.
Now we'll look at the process flow of how milk protein concentrate is manufactured. We take our skim milk, we pasteurize it, then we run it through a ultrafiltration process. This can be used in combination with diafiltration. Diafiltration is adding water back in to dilute out your protein so you can pass it through the membrane again to remove more of your lactose as well as minerals. The retentate of the ultrafiltration process is our UF milk. We can evaporate that to remove more water and spray dry it to remove more water, and then package that finished material. If we look at the composition or Aadpi industrial standards for milk protein concentrate as well as milk protein isolate, you can see we have a wide variety of different protein contents ranging from MPC 40 all the way to milk protein isolate. Our milk protein isolate usually has a minimum protein content of around 89.5%, so usually around 90%, while our MPC 40 has a minimum protein content of around 39.5 or 40. So usually the number behind the MPC, that's what the target protein content within that product. As you can see, as we have higher protein, we have less lactose, so we're removing more of that lactose, as well as to a degree removing more of that mineral or ash.
So Nathan mentioned ADPI. That stands for American Dairy Products Institute. It's a trade association, a national trade association for the dry milk and dry whey industries. They're located in Chicago, and that's why this is what they do. One of the big things they do, they set standards for these various dry milk and dry whey products.
Yep. So now we'll look at the manufacture of dairy ingredients from whey. We'll first look at whey powder. So the basics of whey processing, we're going to remove the fines. That can be a bit detrimental factor for our further processing steps. We don't want to have fines feeding our membrane. We can plug them up quite quickly and have some very high economic losses if we don't remove those fines properly. We also want to remove that whey cream, as we described earlier. Fat can be a detrimental effect in the powder format, as well as the processing leading up to the final powder. We're going to pasteurize that whey. Bleaching is optional, and then storage.
So just a couple notes on that. The fines we're talking about here are cheese fines. So when you're making cheese, some cheese fines, you might think of it as cheese dust, tiny particles of curd escape in the whey, and those are nothing but a problem downstream in whey processing. So we either need to use some kind of filter or mechanical centrifugation to remove those fines. Whey cream removal, we're going to use a separator just like we use for sweet cream on the milk side. Use a separator to remove the whey cream. Now remember, I said earlier on today that in any separation process you have to leverage differences. Well, in this one, with a separator, we're using differences in specific gravity or weight. So cream is like oil. It's lighter than water. It's going to float to the top. So if you put it in a centrifuge, it's going to separate from the skim portion, which is water, because of differences in essentially density. It's less dense. The bleaching step, that's for those cheese plants that use annatto to color their cheese to make, say, colored cheddar or colored Colby cheese. But that color, which is well liked in a number of cheese varieties, but especially cheddar and Colby, is nothing but a pain in the butt on the whey side, because it's going to cause a colored whey that most people aren't going to want to use as an ingredient. So then maybe you can bleach it. Bleaching is like adding it's kind of like adding a form of peroxide to the whey to destroy that color, but there's a problem with that. You destroy the color and the color goes away, but in the process you generate other compounds which some industries, in particular the baby food industry, consider as a big negative. So bleaching is a whole issue unto itself. From a cheese standpoint, color can be a big advantage, cheese making standpoint. From a whey processing standpoint, annatto color in the whey is nothing but a headache.
So some of the processing options for whey, we can concentrate that and make a whole whey powder. We can fractionate that into a whey protein concentrate or whey protein isolate, as well as there are options to convert that into a fuel, fertilizer, For the first process we'll look at is a way to concentrate this. So we're going to take that whey, run through evaporator, and dry it. There is whey protein in this product, so that does have value. But it is still mostly lactose, or approximately 13% protein, as well as 70% lactose.
So what we're talking about here is making sweet whey powder, typically. So we've got our whey. We're not going to fractionate it at all. We're just going to concentrate it to remove water. Typically, today, if you'd start from scratch, you'd first, again, like we talked earlier, go through reverse osmosis, the cheapest way to remove water, followed by evaporation, followed by drying, and to get your sweet whey powder.
So if we look at the process flow for whole whey powder, all the components are in whey except the water. The equipment required for this are evaporation, crystallizing, cooling, as well as spray drying. So we'll take our fluid whey in, we'll run it through our clarification and separator, we'll remove the cheese fines and the whey cream that we described earlier. We'll get our clarified whey, pasteurize it, then we'll go through our evaporation and reverse osmosis unit. Reverse osmosis first, then evaporation. Then we'll crystallize. As a very important area of the manufacture of whole whey powder, getting the correct crystal form, so you'll produce a non-hydroscopic finished powder, and then spray drying, and then packaging.
So one of the things we have here as a byproduct, something called cow water. COW stands for condensate of whey. So when you run whey through an RO system, reverse osmosis, like we talked about earlier, you're going to get a stream of pure water off. We call that cow water. But when you go through an evaporator, you're going to, just like you boil water, you're going to get water vapor off and they recondense it. And that's condensate. So condensate of whey. That was the original cow water. So it's essentially almost distilled water that's gotten either through the reverse osmosis process or for the evaporation process. The crystallization step, like Nathan said, is really critical. What you're doing is you're cooling the concentrated whey, and it causes the lactose to crystallize. It's not 100%, but the higher percent you can get, the better, because if you don't do that and you spray dry it, you're going to get this sticky, gooey mess. You have to form lactose crystals first before you spray dry it, so you get a powder that's not sticky, and it's also not hydroscopic. What does hydroscopic mean? Hydroscopic means it absorbs water out of the air. So if it's a powder is hydroscopic, it'll absorb water out of the air and it'll go from free flowing to almost like a piece of cement or a brick. It's just really, really hard. So there are steps you have to take in this whole process to make that powder, and crystallization is a really important one, to make that powder not hydroscopic, meaning it's not searching to bind with water in the air. Because there's nothing worse than making container loads of sweet whey powder and putting it on a ship and shipping it to China or Korea or somewhere. When it gets there, it's like cement blocks. That's not a happy thing.
Okay, now we'll look at the whole whey. Our first step is our evaporation. We need to supersaturate the lactose so the majority will form crystals. And as we just talked about in the previous slide, this is critical for making a non-hydroscopic powder. We need time to form our alpha lactose crystals, and then for drying we need to have further conversion of our lactose glass to our alpha lactose crystal. And the two-stage dryer is favored in this process.
So what we're talking about here, that glass form of lactose, it's just searching. It's unstable, and it's just searching to suck up water. And that's the type that's going to make a hydroscopic whey powder. But in this process, if you give it time and the right conditions, it'll convert to alpha lactose crystals, which are very stable. They're happy. They don't need water. They don't want any extra water. So if you do it, if you process it in a proper manner to get good conversion to the alpha lactose crystals, it'll be non-hydroscopic. The powder will be free-flowing. It doesn't want to bind to water, so it won't turn to brick on you in the bag or in the tote. Two-stage dryers just give you more time. There's a second stage, often a fluid bed stage, that gives more time to convert the glass form of lactose to the alpha lactose crystal form. So it's really, really a good way, good means to make a non-hydroscopic powder.
Now we'll look at the composition of whole whey powder. The first one we'll talk about is sweet whey. As we said earlier, the typical composition is protein around 13%, moisture 5%, lactose around 73%. Our smallest component is our fat, around 1%, and ash. This usually has a shelf life around 6 to 12 months. You can see the storage conditions of less than 80 degrees Fahrenheit and less than 65 relative humidity. Characteristic of this powder are off-white to cream. Flavor should have a normal whey or a slightly salty flavor. Usually has a pH around 5.7 to 6. If we look at acid whey in comparison, this has a slightly or similar composition, but higher ash. So we have more ash within this product. You want to talk about acid whey a little more?
Yeah, so acid whey, to be honest, there's extremely little acid whey that's dried in the U.S. anymore. Most cheese varieties, think of virtually all your standard ones like cheddar, Colby, Monterey Jack, the various mozzarellas, they're all going to result in sweet whey powders. Acid whey comes from those types of cheeses where a tremendous amount of acid is formed up front in the cheese making process. That would be things like cream cheese and cottage cheese, because they're called acid set cheeses because they're actually coagulated by acid, much like yogurt is. So there's a tremendous amount of acid in those products, and the pH of that whey is very low. It's typically below 5 in that 4.6 to 5.0 range, so it's really acid. Very tough to dry. So a couple things you should know about drying whey. Acid is always your enemy. The more acid that's there, meaning the lower the pH, the more it's going to fight you when you try and process it and dry it. So it's called sweet whey powder for a reason. Sweet meaning less acid in it. The range here that it's talking about is oops, let me see, pointer, 5.7 to 6.0, but the closer you can keep it to 6.0, the better off you're going to be. Nathan just mentioned, well, why, you might wonder, well, why would acid whey powder have more ash in it? Well, what does acid do? Acid dissolves calcium phosphate from the protein casein structure. So there'll be more calcium phosphate in the whey, and correspondingly with acid whey, because of all that acid there, it's going to strip more of the calcium phosphate from the proteins, and there's going to be more of it in the whey. Again, just like acid, ash really fights you when you're trying to dry a powder, so that makes it tough. The other thing, which isn't mentioned in this particular slide, but I'll mention it now, is galactose. So lactose exists. Lactose is a disaccharide. It has two sugars hooked together, glucose and galactose. Well, it turns out the cultures we use to make cheese, some of the cultures don't like the galactose part, so they'll separate the glucose and the galactose. They'll eat the glucose, but they'll leave the galactose in the whey, in the cheese and in the whey, and that builds up, and that's a very sticky sugar, and it doesn't dry well. So whey that is acid is hard to dry. Whey that is high in calcium is hard to dry. Whey that is high in galactose is hard to dry. And an acid whey can often be high in all three at the same time. That's why it's incredibly hard to dry. So there are very few people doing the acid whey, dry acid whey anymore. But back to the sweet whey, which dominates in terms of dried whey powders, still you want to, have the pH high, up in that 6.0 range, not much galactose, and not so much dissolved calcium in the whey, and then it's going to dry a lot better, and the whey powder will perform a lot better for your customers.
Yep. So now we'll get into some of the issues with drying whey and dairy products. Lactic acid is a big factor, especially on the whey side. This is formed during cheese making and is responsible for decreasing our pH and it helps to coagulate milk, and it adds flavor to the final cheese. It is produced by the splitting of lactose into glucose and galactose, and then is converting glucose to lactic acid. It is important that galactose remains in most Italian cultures, and galactose is another thing that indicates stickiness of the powder, tough to dry. While American cultures process galactose differently, and therefore their wheys have lower galactose content. So not all wheys are created equal. The cheese type that is being produced can have a big effect on how difficult or easy it is to manufacture the final whey powder.
Right. So typically in the whey powder industry, the whey that's considered superior to all for drying is Swiss cheese whey, and that's primarily because it's very sweet. There's not much lactic acid there. Like this slide says, lactic acid is sticky. But this slide talks about the American cultures. That American means American style cheeses. That's things like cheddar, Colby, and Monterey Jack. The cultures that we use to make those cheeses pretty much chew up the galactose, so there won't be a lot of residual galactose in the whey, which is a good thing. So whey processors prefer whey from cheddar plants and Colby plants and Monterey Jack plants compared to Italian plants that make cheeses like Parmesan or low moisture part skim or whole milk mozzarella, because they use Italian cultures which generate a lot of galactose in the whey and makes that whey much harder to process and dry.
Another thing that makes drying whey powders difficult is calcium phosphate. This results in calcium precipitation. You can see within this image here pipe and how much of the flow is restricted due to the buildup of calcium phosphate or milkstone. This can decrease evaporation run times. You can coat and block your pipes, which you can see here in the image. This is an insoluble material in the final dry product, so your end consumer isn't going to be happy if they have a bunch of precipitate in the final powder as they're utilizing it for the end application. This also can decrease the flux of RO membranes and increase the time required for an acid cleaning cycle.
So a couple points here. Nathan just mentioned flux with membranes. Flux just means how rapidly the water and other things permeate the membrane. So a decreased flux is a bad thing. It means it's taking longer to do its thing and get more of the water out, or get more of the minerals out, or get more of the lactose out. This slide here in the lower right is interesting. So that, remember I told you earlier on, in an evaporator there's a tube bundle in there, and then the tubes, the product runs inside the tubes in the tube bundle, and the heating medium is outside the tubes. So this is one tube from a tube bundle, and you can see it's so much calcium phosphate is built up in there, it's almost plugged. Well, in evaporators, I've seen it where they completely plug, and that calcium phosphate is like cement in there, and they literally have to get in there with drills and drill it out. But you got to remember, these tube bundles might be 2 stories tall. They're huge. These evaporators are huge. So when you get fouling on the inside of those pipes with this calcium phosphate buildup, like you see in this one tube here, that's a real operational problem, because now your process of evaporating the whey really slows down. Plus, when you get this buildup of calcium lactate in the tubes like you see here, the heat transfer goes to hell on you, because it's got to penetrate not just the wall of the tube, but now this buildup of calcium phosphate there as well to get to the liquid whey that's running through that tube. It really, really slows that down too. So that's nothing but a problem.
The next product we'll look at is a whey protein concentrate. So you can look at this slide here, the different compositions of our various whey protein concentrates. We can see our starting material here of whey with around 13% protein. We run it through an ultrafiltration membrane to remove some of that lactose and increase our protein content. There are whey protein concentrates 34, whey protein concentrate 55, and WPC 80 as well.
So what these numbers stand for, 34, 55, and 80, means the percent protein in the solids that are in those products. So originally WPC 34 was the initial whey protein concentrate that was made in the industry. I'm talking back in the 1970s. Well, why 34? I think because that comes real close to the protein content of non-fat dry milk or skim milk powders, because sometimes in some products whey protein concentrate can substitute for non-fat dry milk or skim milk powders, so they chose an equivalent protein level in that powder. So originally, I'm talking back in the 70s and 80s, the vast majority of WPC was made at the 34% protein level. But now in today's world, they've bumped it up to WPC 55 or even 60, WPC 80, and we'll talk in a minute about WPC 90 or whey protein isolates. Well, why? Well, as you might imagine, the higher the protein, the more dollars you get back for it. But also, on the flip side, the higher you have to go in protein, the more cost there is to get there. So you got to make sure if you're going to go higher, you know your end product's going to give you more. It's going to sell for a higher price, but you got to make sure that higher price covers your extra cost in getting there as well.
So now we'll look at the process flow for producing whey protein concentrate. So we'll take our pasteurized fluid whey, we'll go through our ultrafiltration process, we'll permeate our lactose and our minerals, and we'll retain our protein, and then we can spray dry that product.
So I should have made this point earlier, but we're going through these membranes. We're not removing all of the water by a long shot. We're not removing all of the minerals. We're not removing all of the lactose. We're removing some of them, because as we go down this line here, that's still a liquid, and it still has water in, it still has some lactose in, it still has some minerals in. But the way we get to a higher protein content is we keep taking more of the minerals out and more of the lactose out by the steps we take in processing.
And as we go to a higher protein concentrate, the previous slide we were at 34 to 50%. Now we're looking at 50 to 80%. We'll have to add an additional step in called our diafiltration. So we add water back into our product to help solubilize more of the protein, or not protein, not calcium either, lactose. We solubilize our lactose and be able to permeate through that membrane.
So think of it this way, diafiltration, like Nathan said, it's just adding, so you concentrate it, but you get to a certain point where it's so viscous you can't get any more of the lactose out or any more of the minerals out. So now you take this, it's kind of thick, it's kind of viscous, you take that, now you add a bunch of water to it, so now it's thin again, and now you pass it through the membranes again, and now it takes even more of the lactose out and more of the minerals out because you've added extra water to thin out the whey concentrate. And now you can go through another series of membranes and you'll get more of the lactose and more of the minerals out.
Yep. This slide basically sums up what we just said. So a quick word on WPI, how that is produced. We can produce this in two different ways. We can run it through microfiltration to remove our whey cream in this example. That's also can be removed with a separator. Then we do our ultrafiltration diafiltration step, and then concentrate and spray dry. This also can be produced with ion exchange. So we add a resin in within a vessel. The protein will absorb to that resin. Then we'll be able to desorb that protein, and then we can further concentrate that with UF or another ion filtration step, depending on the final product you're trying to produce.
So these are the two methods that the industry uses. There's one major player that uses this method. The majority of other players use this method. These ion exchange, think of that as very similar in concept to your water softeners at home. They have all these little resin beads in, and the protein molecules are charged. They have a charge to them. I believe they're primarily negative charge, but So they'll stick to those membranes, or stick to those beads, I'm sorry, stick to those ion exchange beads. And then you take off everything else and you put a solution through that unsticks them, which is desorption or desorbed proteins, and then you continue down through this process. So it's two different technologies to end up with kind of very similar, but not totally similar end products. Similar in protein content, but not totally similar in total makeup.
Yeah, you can remove some more of the minerals with the ion exchange method compared to the membrane method. If we look at the composition of whey protein isolate, our minimum protein content is 89.5, so we're usually in between 90 and 92% protein. Our lactose content is quite low. Doing the additional diet filtration step, we're able to permeate most of that lactose through our membranes. Ash usually around 2 to 3%, fat 0.5 to 1, and our moisture around 4 to 5.
So just a little sidetrack here, which we haven't talked about. Maybe they will in some other lectures, but why are these whey proteins so valuable? I would state to you that the primary reason is they're some of the highest quality proteins known to man. Why are they high quality? Because they have a very good balance of their amino acids that make up the proteins, so they are just super nutritious. That's why they're used so much in infant formula. That's why they're used so much in athletic foods for muscle repair and muscle building and things like that, because they are just super good proteins, super quality proteins for muscle growth and muscle repair and things like that. So that's one of the main reasons why they're so very valuable. But as you hear, I think probably in some other lectures, they're also very functional proteins for things like foaming and emulsions and things like that, which is also important. But I think the key driver is they're just nutritionally so darn good.
So now we'll get into some lactose-related products. So what is lactose? Well, it is a disaccharide composed of glucose and galactose. It comes in two different forms, our alpha and beta form. The typical forms are usually our alpha monohydrate and our anhydrous beta. And an amorphous glass mixture of both are alpha and beta. Lactose is not as sweet or as soluble as other sugars and has limited solubility compared to other. We can break this down with an enzyme called lactase into glucose and galactose. And there are quite a few different dairy products that utilize that technique to produce a final beverage.
So just a reminder again, it's the alpha monohydrate that's stable. That'll give you a non-hydroscopic finished product. It's this amorphous glass mixture of alpha and this anhydrous beta. Anhydrous means no water present. So what does that mean? It's looking to bind to water. Here it's already satisfied its hunger for water, and it's got one water molecule bound to it. But here it's anhydrous. It doesn't have any water. Now you might be thinking it makes sense to me that something that's anhydrous is meaning no water present, won't be very sticky. But in this case, because it's anhydrous, it's just searching its environment to bind to it. It wants to bind desperately to a one molecule of water. And that's why it's hydroscopic and will form a brick on you in a bag or tote. Here it's already found its molecule of water. It's happy, it's stable, and it'll stay free-flowing.
We looked at some lactose and related products. Our crystalline lactose or our alpha lactose can be used in the industrial applications, food applications, as well as pharmaceutical applications for filler and pills and so forth. Permeate, this isn't specifically, it contains a lot of lactose, but the term lactose and permeate are kind of interchangeable within the industry, but this is talking about the permeate from our ultrafiltration membranes, as well as beta lactose and amorphous lactose are some related products produced from lactose.
So just so you know, in case you're not familiar, in whey and whey products, the proteins, like we've talked about repeatedly, are very valuable. That's what everybody wants. The fat has a lot of value. Hopefully you can capture it, separate it out as cream. Lactose kind of is up and down in terms of the market value of it, and a lot of times it's not worth very much. And if there's one component of whey that's in surplus in terms of the demand for it in our world, in our food world, it's lactose. So lactose can be a negative drag on value because it's many times it's in total surplus in the marketplace. Sometimes it can actually even be just difficult to get rid of in terms of trying to sell it.
We'll look at the manufacture of milk permeate. So we take our skim milk, pasteurize it. Then we go through the ultrafiltration or dye filtration step. We get that permeate out, which contains our lactose and our ash. We run it through evaporation step. We do have to do crystallization on this product to prevent the beta form from being produced and get that stable alpha form, spray drying, and then packaging.
So, as you might imagine, milk permeate and whey permeate can both be somewhat difficult to dry because you don't have the proteins there, which proteins dry pretty easily, but it's the lactose and the ash, and if there's any, you won't have much acid in milk permeate, you will in whey permeate, but those are what makes things difficult to dry. So drying permeates can be a real task. So this slide is going to talk about production of lactose and permeate. So there's not too many players left anymore that do this, but you can take your pasteurized fluid whey, crystallize the lactose out of it, ultimately wash the crystals and make a pure lactose, dried lactose. But when your starting point is fluid whey, and take some of the lactose out, what's left is typically dried. It's called a reduced lactose whey powder. It's got the protein in it, but it's got less lactose. The common name we use for this in the industry is D-Lac, and that's used a lot for things like cold packed cheese spreads and things like that. Only a couple players are still doing that. Another way to make lactose is to take that permeate, run it through evaporation, first reverse osmosis, then evaporation, crystallize it. You get lactose out of it. You wash it, and you get lactose. Or you can take that permeate, concentrate it through reverse osmosis, concentrate it then through evaporation, crystallize it, and dry it as is, and then you get dairy product solids, okay, which is just essentially dried permeate. So this is dried permeate. So dairy product solids has lactose in, and it has ash in. This is pure lactose. It's only pure lactose crystals. This is reduced lactose whey powder. It's got all the protein from the whey in it, but it's got reduced, and it's got a fair amount of, it's got the ash in it yet, the minerals, but it's got quite a bit, but not all of the lactose removed. So those are three different processes to come up with those three different products. By the way, the dairy product solids, the dried permeate, an awful lot of that powder is going to get exported to Asia, where an awful lot of it's going to be used as a component in various animal feeds, like baby pig feed, baby chicken, baby calf feeds, things like that. Lactose, a lot of that is used in the pharmaceutical industry and in the infant formula industry for energy, for the sugar, but in the pharmaceutical grade lactose, that's used to make pills. So it's like the pill, it's like the stuff in the pill that adds bulk to it, the medicine that's in the pill, so they can make a pill out of it.
So now we'll look at some of the composition of our different products that we can produce from permeate. We have our milk permeate, which contains, this is on a liquid basis here, so around 4.9% lactose, good amount of ash, around 0.45, a little bit of protein. With our milk permeate, we have our lowest concentration of calcium and no lactic acid. If we look at our sweet whey permeate, this contains our lactic acid from the byproduct of cheese making, similar solids, a little bit more ash, and a little bit higher protein similar calcium content there too. If we look at our acid whey permeate, we have our lower solids, higher ash, as Dean was saying. We solubilize more of the calcium or minerals during the cheese making process with these high acid cheeses, and our highest amount of lactic acid. And as that calcium was solubilized, we have quite a bit of calcium in that product.
So you might be wondering, oh, wait a second, we went through these membranes, why is there any protein in? Well, it turns out there isn't, okay? You just told us there is, and now you're saying there isn't. Well, this says crude protein. Well, the way you measure protein in any food is you actually determine how much nitrogen is in the food and then convert it by a multiplication factor into protein. Well, none of this is actually true protein, meaning actual protein. There are a few other compounds in milk, like ammonia, that contain nitrogen that will pass through the membrane and urea and pass through the membrane and get into the permeate, whether it's whey permeate or milk permeate. So this represents nitrogen from actually non-protein sources like urea, like ammonia. But when you still convert it by that factor, and then they call it crude protein, but it's really not protein at all. It is nitrogen containing compounds, but it's not actual protein.
Yep. So we do have some caution. Many producers or products are not defined, so there's other methods of manufacture are possible. If you do produce them in different ways, that can affect the functionality, as well as slight changes in the composition of those final products. As well as some products may contain either milk or whey. So just something to consider.
So what Nathan is saying here is we've showed you today the classic ways of making these products, but sometimes people will make it by kind of an alternate way. So they might buy the different components. So technically you could blend together, some permeate and some lactose and some this and some that, and come up with some of these products by kind of dry blending processes. And technically they might meet the standards for these, but they're really kind of different products. So that's why you have to be a little bit cautious to make sure the product that you're buying is what you think it is, not just compositionally, but also procedurally, how they actually made it, because it can make a difference in how the final product performs.
So in summary, milk is a powerful source of ingredients. We brought milk in and we kind of fractionated out into a wide variety of different products: our milk protein concentrate, isolate, whey protein concentrate and isolate, as well as our non-fat dry milk. And we also looked at the lactose component. The nutritional and functional quantities of dairy ingredients are critical across all food applications. The main processes that we looked at today are water removal and fractionation, and they are essential for the dairy industry to extend shelf life as well as reduce shipping costs. And the composition of dairy ingredients is affected by the processing during their manufacturing, so that is a critical step to consider if you're trying to use a dairy ingredient in your end application.
Yeah, the last thing I'll say is it's an ever changing area, and it's progressing into other components and fractions that they're trying to get out of it. So we talked about the different proteins in there and stuff. So there's methods now where there's different types of casings, which we didn't talk about today. But there's membrane techniques to try and separate, alpha casein from beta casein and things like that. There are other minor proteins in whey and milk, things like lactoperoxidase, which is here. Here, just a little bit. I think this is from
a gallon of milk. That's how much lactoperoxidase it would be. So there's very small amount.
Lactoferrin, which has some really unique functional nutritional properties. Just a little tidbit of that, and CMP, which stands for, I can't remember.
Glycomacropeptide.
Oh, GMP, glycomacropeptide, which is important nutrition for people with phenylketonuria. There's some of that in there as well. So as we keep progressing in this area, I would look for even more very specific proteins and compounds that we're fractionating out of whey and milk for even higher value components for the marketplace.
So with that, thanks for attending. If you have any questions, feel free to send an email to me and we'll get them answered for you throughout the webinar.